Chapter 9 covers stoichiometry. Make sure that you know this definition for the test. It's the study of quantities of materials consumed and produced in chemical reactions. With stoichiometry, we can compare various reactants and products within a balanced chemical equation. In order to successfully complete stoichiometry problems, you have to start with a balanced chemical equation. This follows the law of conservation of mass. In this example of a balanced chemical equation of the decomposition of aluminum oxide, the coefficients represent the number of moles of each. These are used for the comparisons. A mole ratio is a conversion factor. It is based on the coefficients from the balanced chemical equation. It's the step that we use to switch from talking about one substance to another substance from the equation. In our aluminum oxide decomposition example, here are some of the mole ratios that can be extracted from that equation. Since the coefficient with aluminum oxide is 2, and the coefficient with aluminum is 4, a mole ratio would be 2 moles aluminum oxide per 4 moles of aluminum. The inverse is also true. Let's look through an example. In this case, starting with 4 moles of aluminum oxide, the question is, how many moles of aluminum would be produced? As you can see from the dimensional analysis that's set up, the given is the first bracket. The mole ratio comparing aluminum to aluminum oxide is the second step. It's set up in such a way that aluminum oxide will cancel, and the final answer will be left in moles of aluminum, which answers the question. This is the same problem, except now it's satisfying the answer of how many moles of oxygen instead of aluminum. The mole ratio comes from the coefficients for oxygen and aluminum oxide. In order to complete some of these stoichiometrical problems, you need molar mass. Molar mass is the number that we get from the periodic table. It's the mass in grams of 1 mole of a compound. It is expressed to the nearest hundredth, 2 decimal places. Here are some examples. In this question, still using the same balanced chemical equation of the decomposition of aluminum oxide, the starting material is 25.2 grams of aluminum oxide. The question is how many grams of oxygen when they ask for what is the mass of oxygen produced. These mass-to-mass conversions require more steps. Starting with the given, the next step is the molar mass of aluminum oxide, where the masses of 2 aluminum and 3 oxygen have been added together and expressed as 1 mole of that substance. It's arranged so that the mass of the aluminum oxide units will cancel out. The next step is the conversion from talking about aluminum oxide to stating the expression in terms of oxygen. This molar ratio comes from the balanced chemical equation. The numbers are the coefficients from the equation. The final step is a return to the periodic table, where we find the mass of diatomic oxygen. This mass of 2 oxygens, 32.00 grams, is the mass of 1 mole of that substance. The final answer is 11.9 grams of oxygen. This is achieved by multiplying each expression across the top and dividing every expression across the bottom. So let's review the procedure. Step 1, balance the equation. Step 2, consider the mole ratios based on the coefficients from balancing the equation. Step 3, do the dimensional analysis, starting with the given information and working toward the question that's asked. A careful analysis of the units of the given and the required will be a clue as to how many steps are required. Here's another example. Both of these are based on the same balanced chemical equation, but starting with different starting materials. Again, with the same equation, our beginning material is the mass of hydrogen gas, and we're solving for the mass of ammonia. Notice this is a four-step problem. Step 1 is the given. Step 2 is the molar mass of hydrogen gas. Step 3 is the molar ratio to go from hydrogen to ammonia. And the final step is the molar mass of ammonia. And yet another example. In this one, going from the mass of nitrogen gas to the mass of ammonia. Notice that the step sequence is identical. In this unit in stoichiometry, we're dealing with two types of problems, both based on balanced chemical equations. We can either calculate the number of moles of one substance in a formula to the moles of another substance in the formula, or we can do mass to mass, where we're given a quantity of a substance and we can calculate the mass of another substance within that same process. Here's the basic roadmap. When working a mole-to-mole problem, you take the moles given, you use a mole ratio step, and that gives you your answer. These are very simple problems, just 2 steps. Whereas a mass-to-mass problem is a 4-step problem. You start with the mass of the given substance, use the molar mass in the periodic table to convert that to moles, use a mole ratio to swap substances, and then do the 4th step of another molar mass of the final substance to gain the answer. Based on the steps described, let's solve this problem. How many moles of lithium hydroxide react with 20.0 moles of carbon dioxide, the average amount exhaled by a human each day? First, we need to balance this equation. There's an imbalance in the number of lithiums, so we'll put a 2 in front of lithium hydroxide. That increases our number of oxygens and hydrogens, which balance out by the water molecule in the products. The next step is to identify the molar ratios. The comparison of moles of carbon dioxide to moles of lithium hydroxide are based on the coefficients. This equation indicates that there's 1 mole of carbon dioxide for every 2 moles of lithium hydroxide. To set up the dimensional analysis, we begin with our given information, and we use this mole ratio, setting up moles of carbon dioxide in the denominator so that it will cancel, moles of lithium in the denominator because that's the question we're trying to answer, and then filling in those molar amounts. So if moles of carbon dioxide cancel, we have an answer in moles of lithium. The correct number of significant digits, which is 3, matching the given information, the answer to this question is 40.0 moles of lithium hydroxide. In this example, we have the decomposition of potassium chlorate. The given information is moles of oxygen gas, and the desired information is moles of potassium chlorate. First, we need to balance the equation. I can see that the oxygen has one of those 3-2 disagreements. So I'll start by swapping those numbers so that I have a total of 6 oxygens on both sides. The final will be to put a 2 in front of potassium chloride so that we have the same numbers on both sides. Now this particular question deals with the oxygen and the potassium chlorate. So our mole ratio will consist of those 2 substances. The given information is 15 moles of O2. These mole-mole problems are 2-step problems, so the only other step is the mole ratio. We put moles of oxygen on the bottom so that it'll cancel. We put moles of potassium chlorate on the top because that's the desired unit. We get the numbers from the balanced chemical equation. We just need to put them in the right spots now that we have the units in the correct spots. 3 moles of oxygen, 2 moles of potassium chlorate. Multiply across the top, divide across the bottom.
The final answer is 10. Since we need that expressed in two significant digits, we'll put a decimal, and that would be 10 mole of potassium chlorate for the final answer.
I hope that at this point you feel a little more comfortable with stoichiometry. Good luck.